Hello, everyone. This is lecture 6 of PTRE 465 and 531, Petroleum Reservoir Geomechanics. Today we'll proceed with Module 1, the subsurface stress state. Last time, it was a pretty heavy class, lecture 5. We learned a lot of new stuff. We went through the stress state in an arbitrary system, oriented arbitrarily in a configuration where the coordinates are arbitrarily oriented in space. We talked a little bit about that, which is a pretty complex mathematically concept. We talked about Euler's matrix for the rotation of the coordinates, the matrix transformation. We didn't use it yet in an example problem, but you have seen how it looks like. Let me just show it. We talked about, yeah, this ugly RPG, and you can use it to go from a geographical, like random, arbitrarily oriented coordinate system to the principal and vice versa, using those two equations. And then we started simplifying the process. We basically make an overview of the Andersonian faulting stress regime. We force one of the principal axes to be vertical, which made the other two horizontal. And the other rule that we applied is that SH max is the most compressive of the two horizontal stresses. Sometimes, if you see the word confinement, confining, or horizontal confining, it involves the horizontal stresses. And if you see the word overburden, think of SV. It means the vertical. So when you see confinement, you think of SH max and SH mean. When you see overburden, you think of SV. That set of rules created three possible permutations. We had the Andersonian faulting regimes. The first one is the normal faulting, the most common. You have that in the Gulf of Mexico. Most places around the earth, they are normal faulting, including more or less where we stand here in North Dakota is normal-ish faulting stress regime. Then we have reverse or thrust faulting, which is the opposite. That's what you have near mountains, like the Himalayas, great example. New England, actually, in the US, good example, the East Coast. And then we have the strike slip, which is a little bit of in between. Classic example, the San Andreas fault. A big part of the west coast of the US is strike slip faulting. Some areas near where we are now in North Dakota are sort of in the between normal faulting and strike slip, etc., etc. And we use footwall and hanging wall blocks to visualize it. And we said about the configurations in each of them. Like for the normal faulting, SV is the strongest, which is obviously above. And then you have the SH max, which is the stronger of the two horizontal, obviously, behind the blocks pushing them. Sorry, not behind the blocks, in between. And you have the least one behind the blocks. So basically what I'm trying to explain is this, that SV is always understandable where it is, but where is the pen? For normal faulting, this was SH mean, and what is left in the mean is the intermediate one, which would be SH max. For strike slip faulting is the other way around. You have SH mean being the intermediate, and then you have SH max pushing, which is the strongest, the most compressive of all, and certainly of the two horizontal, SH, capital H, max. Let me write it again. It's capital H, max, pushing the foot wall, the hanging wall, to slide on top of the foot wall and basically create a mountain, let's say, over the broad context. Strike slip is a little bit more weird. You need to think about basically the motion is done in the direction of SH. Oh, no, sorry, wrong colors. The motion is done in the direction of SH max. And then the weakest one would be SH mean. And of course, in all of them, the SV is vertical. SV, SV, SV. You need to know this stuff, and you need to not only know them necessarily by memory, but have them understood in your mind. And I think some of you already know about this concept. Okay, and then we try to put everything into one number, and this is equation by Simpson, 1997, is not necessarily something that has a physical meaning or a direct physical meaning, but it's very easy to basically collapse everything, your stress state, into one number. You give me one number, and I know what your stress state is. And basically alpha phi, it's a long equation, but it's not hard to apply, and will vary according to what your stress regime is. And then you plug in the appropriate S1, the appropriate S3, the appropriate S2, and you find a value that can vary from alpha phi, a value of alpha phi, which can vary from 0, very, very strong normal faulting stress state, to 3, very, very strong reverse faulting stress state. And then somebody took advantage, Dr. Lundstern took advantage of this color scheme, of this scale, to convert that to a color scheme and color his beautiful maps accordingly to basically the stress state. Some of you may have seen the old world stress map, and this one is a better version because it uses color to visualize the local stress regime. And obviously, there are places where, as you go deeper, the regime might change. And as you see, the East Coast is very red because it's reverse faulting. The portion of the West Coast is yellowish, greenish. It's mostly strike slip, very well-known strike slip region. The Midwest, greenish blue. Yeah, and then Texas is mostly blue. And Canada, yeah, it's orangey, green. Part of it is actually red. And when we say this region is very tectonically active versus tectonically relaxed, when it's tectonically active, you expect a lot of mountains forming, a lot of faults, etc. You will think reverse faulting, maybe strike slip faulting. But a tectonically relaxed area would be normal, very, very normal. Like Gulf of Mexico is very normal faulting. And we are going to see later, not today, later lectures in this module, why this is the case. It has to do with the depositional environment in place. San Andreas fault, or West Coast in general is a tectonically active area, very well known tectonically active area because the horizontal stresses are much stronger than the vertical, the overburden stress. So that's the difference between tectonically active and tectonically relaxed. And those who took advanced drilling with me, they have seen that before, maybe not in that great depth, but they have. All right. Now, we went from a very complicated version of a problem using the Euler's matrix to a very simplified version using the Andersonian theory, the Anderson's 1951 theory. Now I'm going to combine the two. I'm going to get somewhere at an intermediate level. How can I use the Andersonian theory to simplify Euler's matrix? So when I use it in an example problem, in my homework, in my exam, in class, I will get, I will have a version that is not terrible to use mathematically, but it's also not very, very idealistic. So I'm trying to get in the middle between the two, in the middle between the, in terms of complexity. Okay. So simplification of the rotation matrix for Andersonian environments. We talk about three angles, right? Alpha, beta, and gamma. Now, normal faulting has a set of criteria. SV must be bigger than SH max, which is bigger than SH min. For those, all the normal faulting stress state, alpha would be the azimuth of SH min, the angle of SH min from north, basically, from the indication of the north. Beta would be 90. Why is beta 90? Because beta is, because SV is completely vertical, and gamma would be, as a result, would be 0. So if I take these values, these angles, and I put them into the Euler's matrix somewhere here, I will simplify it to this point. It will become simplified to this, okay? The RPG matrix. This is a much easier matrix to work with than what we have seen before. The version that we see, the general version that we saw before. In fact, it can get much more complicated than that version as well. For reverse faulting, alpha becomes the azimuth of SH max, beta becomes 0, and gamma also becomes 0. So the RPG simplifies to this version. Of course, I have alpha, I have sine alpha, and everywhere else I have 0 and 1. Sort of like the one above it, but of course they are not the same matrices. This is a much easier matrix to deal with. What about strike slip? Alpha is again the azimuth of SH max, because now SH max is S1, beta is 0, gamma is 90. And there are other formats you can use. You can use a different set of angles from a different reference, from different reference points, or taken in a different way. It will change the Euler matrix. But if you use the angles correctly, it may be different angles, it can still work. It's a mathematical, it's a geometrical or a trigonometric problem, I guess. The result is this. Again, cos alpha, sine alpha, zeros and ones. Okay, and that's much easier to use. But let's do some example problems to understand understand how to use them. Okay, the equations, we are gonna use them as the same as we learned before. These ones, these two, this one, and this one. But it's gonna be an easier version, which is good. Example problem number 2. Calculate the stress tensor S for a normal faulting stress state with S1 equals 3000 psi, S2 is 2500 psi, and S3 is 2000 psi, knowing that the azimuth of SH mean is in the north-south direction, and that the SV is one of the principal stresses. So basically it tells me it's an Andersonian faulting. It's an Andersonian stress regime, excuse me. Okay, so alpha is taken from clockwise from to S1 from north. Beta is from the flat point all the way up to S1. Hey. Gamma is the inclination, basically. And I will take, these are the angles. Alpha is 0 because, what is it? The azimuth of SH mean is, the azimuth of SH mean is in the north-south direction. And SV is one of the principal stresses. Beta is 90 and gamma is 0. I don't need that because I know that is, I know that is normal faulting stress state. So if I go back, normal faulting stress state, I have alpha, the azimuth of SH mean, beta is 90, gamma is 0. So I come here, I plug in those values to the Eulers, and my RPG matrix becomes even more simple because now I have sine of alpha is 0, cos of alpha is 90. Cos of alpha is 1. So I further simplify my RPG from what I saw in the previous 2 slides ago to this one that has zeros and ones and -1. And now my SP matrix, which is the principal stress matrix, would be in the form of, as we learned before. Oh, it would be in this form. SP as the principal stresses. I know that SV is a principal stress, and I have Andersonian faulting stress state is S1, S2, S3. Okay, everything else is 0. The biggest of the 3 is the S1, 3000, comes here. The middle is, the intermediate is 2500, S3 is 2000. So I have my SP, I have my RPG, I want to find my S. The stress tensor S. So now I input the equation from that slide with the Euler matrix. I basically have RPG transpose. If you see, if you have slide version that has -1 instead of T, it's wrong. You don't have the most updated version. So bear in mind, this is T. If you have the one that says -1, you don't have the latest version. The numbers. Yeah, that's different. How do I transpose a matrix? Is I go, the number of rows becomes the number of columns. And it goes like this, like as if I have a mirror, like here. And whatever I see on one side, I move it basically against. If I have row I, column J, it becomes row J, column I, the other way. If it's inverse, it's you need to make it such that you multiply the two and you get the identity matrix. In MATLAB, to get the inverse of a matrix, you write INV, parenthesis, the name of the matrix. To get the transpose, you just put apostrophe. That's why sometimes it's confusing, very confusing to me as well, with the raised to the power of -1, which really means inverse. Anyway, I have the transpose of RPG, the matrix of the principal stresses, which was very easy to get, S1, S2, S3, because we know that those are principal stresses. And then again, times the RPG without it being transposed. So here is transposed, not yet transposed, but it will be. This one will stay as is. And the way we do it is that I go from left to right. Well, I need one step first. I need to transpose the first one. So now it's transposed, and I need to take my time and go like this. Let's see. Take this, multiply by, sorry. What did I do? Oh, there you go. Multiply by this, add this times this, add this times this. And then take this, multiply by this, plus this, multiply by this, plus this, multiply by this. And then you basically have a new matrix where basically, yeah, it would be, what you find is basically, okay, I did with orange, I did the first row times the first column. So it's gonna be first row, first column. Yeah. The fact that you have zeros, it helps a lot. Then you have second row, second column, right? Goes on like this. And you are gonna have a new matrix that is 3 by 3, and you are gonna multiply the new one with the last matrix that we have here. So this one will come here, multiply again the same way. And if you do it correctly, the answer would be like this. So basically, we reversed the order of the original 3,000, 2,500, 2,000 became 2,000, 2,500 to. Now, quick trick question is, which is the, in terms of SV, SH max and SH mean, which is the SV? What is the SH max and what is the SH mean?
Depends on the stresses you are.
Yeah.
It's normal faulting, basically.
Yeah. It gave you, the question gave you that answer, right? So that's one way of measuring of setting up a matrix, is having SH mean, SH max, SV. So, but this is not this is S.
Yes.
Yeah, it's S. Because SP is S1, S2, S3, etc., etc. Okay. Example problem number 3. What did we do here? Yeah, but I didn't. I shouldn't have everything show up immediately. I don't know why it was in the animation. But anyway, calculate the stress tensor S for a strike slip faulting stress state with S1 now 3,000, S2 2,500, S3 2,000. So the same as before, but now it's a strike slip faulting stress state. And you know that the azimuth of SH max is in the north-south direction, and that SV is one of the principal stresses. So now my alpha is 0, my beta is 0, my gamma is 90. My SP remains the same. My RPG now is different, slightly different. Like again, I said before, I take the 3 angles, I input them into the RPG matrix, and then I basically simplify as much as I can, and I will arrive to these values. Again, the same map here. Basically, it's a little bit complicated to understand it, but it's easy to get it like you have the right hand rule, and imagine you have a right hand on top of another right hand, and then you move one of the hands, and you have to find the angles between each finger, like the imagine another person's right hand, yeah, beneath yours, and you move only the top one. That's how you get the angles. You have the alpha is on the. It's better if you imagine it only on one plane every time.
How about S3? There is no angle for S3?
They move all together.
They move all together.
It's like there is 90 degrees.
Okay.
between them.
Yeah, there is the inclination gamma.
Okay. Okay,
Yeah.
so that's enough.
Yeah.
If you define two vectors, then the.
Well, gamma is the same if you come the other way. Because they are all at 90 degrees with each other. So again, you set up your matrix, you transpose, you said it correctly, then you transpose. And then you multiply, and you now find 3,000, 22,000, 2,500. Okay. And again, a good question is what is SH max? What is SH min? What is SV?
Like sleep basic.
Yeah. So 3,000 is SH max. SV.
SV is
So
200.
do you have to
2000.
define the stress regime first, or you have to see?
It was part of the question. It was saying it here.
Okay, yes.
So I didn't need to tell you, I mean, you already knew that it was
Yeah.
that, but SP is set always S1, S2, S3. S can vary how it can be, you may have shear stresses. I mean, you don't have in this case.
There is two types of strike sleeps. There is like strike sleeps where you have like a compression, like with the
Yeah.
horizontal SHME max, and you have like strike sleep that is like reversed, which is like a normal folding, but with a
Or oblique.
Yeah,
Oblique.
it's like there is like this, like you compress and you move like this,
Yeah.
or you're like stretch and move like this.
Yeah, well, last time we talked about two types of strike slip, the sinistral and the dextral.
Sinistral depends on the movement. So if
Yeah,
you have
yeah.
the left compartment go farther, this is dextral.
Yeah.
And if it's like
No, the left is sinistral.
it's like this and this, basically. It's
Yeah,
with
like you stand on one, you see the other one going to the
Yeah.
left.
yes, that's sinistral.
Yeah, and then you stand on the other one, everything goes to the
Yeah.
right, is dextra.
Yeah.
Yeah, it's from Greek words, that's why.
Okay. Because they taught us like the dextral it goes with like
The clock,
the
yeah, that's correct,
clockwise,
that's
it's
correct.
Clockwise and sinistral.
Yeah,
is
that's correct,
reverse
that's correct.
clockwise,
Yeah.
Mhm.
Yeah, if you stand on one side, you see the other
Yeah.
moving the other way. Yeah, very nice. Yeah, oblique faults are mixture. You have
Yeah.
components.
They
Yeah.
call it composite fault.
Yeah. It can be very complicated
Yeah,
actually,
yeah.
and in different areas. Very
Sometimes you have
complex.
really models of fractures where you have like 4 types of faults, they move all together, for
Yeah, like a graben.
For example, yeah, it gives graben,
Yeah.
it gives like reverse faulting, like it's like
Yeah.
because you have shear, like movements, like
Or
because
horse.
yeah,
If it's a mountain. or
yeah, horse and graben.
Yeah.
It's like stairs basically.
Yeah.
That's when you are forming like an ocean.
Yeah.
At the beginning, you will have like rifting stage where you can see the horse and graben, and it's gonna keep going farther. Then you
Yeah,
have, like,
become deeper and more wider, and eventually you have a basin. Yeah.
yeah, and you will have carbonate precipitation.
Oh.
At the beginning, you will have just like fluvial, like sandstones and breccia, conglomerates at the beginning.
Yeah.
When it develop to sea, so you will have like carbonates coming in the top.
Yeah, that's
And
true.
when it's a reverse cycle, you're closing. So the thing is that when you are compressing like this, the ocean gonna be like more deeper, so you cannot form any carbonates at that level. So you will have more shape.
Yeah, if it's compressed, it's more tectonically active, right? Yeah.
Yeah.
Yeah, it can get very complicated.
Yeah. That's the thing,
With
like
time.
how you can like do this in those areas.
Yeah, I mean, you have to be able to model backwards. Yeah.
It's long,
Yeah, it's a long process. But that's how you find the faults and the traps for oil.
oh, yeah,
Uh,
oh, yeah. It's more important, but what people think.
yeah, very important. So, oops, sorry. I don't know why I broke down the animation system.
Yeah,
It doesn't go on.
by the way, the SP is like, I was like, I missed that, but to be honest, the SP.
Oh, SP is the principal stresses matrix. So
stress P, okay.
everything should be zero in the shear except the S1, S2, S3.
Oh,
So this is basically S1, this is S2, this is S3. Always, always, always. But the S can vary.
the RPG is different.
RPG is the Euler matrix. Euler matrix for the rotation. Yeah.
Okay. Oh, you're trying to feed that on, okay.
Yeah, Euler matrix is in the slides before.
Okay.
Let me-
Yeah.
1 second. Euler matrix is this one. But you have for different, you see it's complicated, but you have different values, alpha, beta, gamma for every stress regime. And it simplifies it. It looks complicated now, but look at in our example problem, where is it for?
So you have the alpha and you have, okay, that's why it's 0, 0.
Yeah, it became easy now.
Yeah, 0.
It became easy. Of course, it might take a while to get to that, but
Understand it.
yeah, S1, S2, SP is always zeros, and S1, S2, S3.
Yeah.
Always, always, always. S can be anything, you know, it can be anything you want. But basically here we have the same problem, but reverse faulting stress state, same numbers. Now SH max is in the east-west direction. And SV is one of the principal stresses again. And the last part is a little bit redundant. I mean, because if we call it SV, it sort of expects to be one of the principal stresses. And we have here the same angles, now reverse faulting. So, where is it? 90 degrees alpha, 0, 0. So, I mean, for all our, basically it tells you SV is one of the principal stresses. Imagine S3 being touching the black line, basically. You set them up. This is SP, and you find S, same way. And now we have 2,500, 3,000, 2,000. And that is a, basically now it's, what is it? SH min, SH max, SV. If I'm not, yeah. 2,000 is the SV, 3,000 is the SH max.
So what's the role of S? Since we have SP and we know the stress regime.
S is the arbitrary, it's like the system that you said is the stress tensor. SP is the principal. S may not have zeros here, may have shear.
Yes.
It's idealistic, this one, it's an easy example, that's why. But SP, the principal, which is what you have here, this one is principal SP, has only normal stresses, principal directions. So it's zero everywhere except the diagonal. But these examples are very idealistic because it's like normal faulting, strike slip faulting, reverse faulting.
Yeah,
It's
but
very.
since we have the same regime, why and we have SP and we know what's SH mean, what this is much because the stress regime is already defined. So
Okay.
why we have S? Why we are looking for S?
Because I want to basically find the stress field with the coordinate system that I have defined.
Oh, okay.
I don't want to know the principal stresses. I want to know the stress state with the system that I defined. I can make another coordinate system as I like. That
Like the new IGK, right?
Yeah, yeah, yeah.
Okay.
If you want to quantify to a block that you want, yeah. and
Yeah.
We talked about that in the previous picture.
If I wanted to make it more complicated, then I would have shears here, for instance. But basically it gets in between basically random stress state and normal Andersonian, which is the easiest type, you know, like, so I'm showing how we can use the RPG to make without having a very complicated version of the RPG. RPG is known as the Euler's matrix. And it's like
It's like to convert the system, right?
yeah. Because alpha, beta, and gamma are very easy angles that we are using in these problems. So they take this, where is it? Sorry. This one, it makes it very easy matrix, right? But it can be alpha equals 45 or 50. It can be very weird numbers. It can be very weird. In fact, you're gonna see a weird, slightly weird one. For example, problem number 5 later on. Oh, yeah, now, I guess. Okay, calculate the stress tensor S for a strike slip faulting stress state with S1 equals 300,000, S2 2,500, and S3 2,000, knowing that the azimuth of SH max is no longer in the east, in the north-south direction as it was before. Now it's 135. And the SV is one of the principal stresses. So now my alpha is no longer, what was it for strike slip? Was it 0?
Was it 0,090?
Yeah, now it's 135. So I change one of them. Automatically, my RPG becomes.
You need to find the RPG with cos alpha and cos alpha minus beta.
Yeah, it's a weird number. This is like square root of 2 over 2. 0.707 is square root of 2 over 2, I believe. So now my RPG is weird.
It's minus cos 45.
Yeah. And which is basically the same as, subtract. But the SP remains the same, huh? S1, S2, S3, everything else.
Same example, just with a different.
Yeah, I just made the RPG slightly harder. You solve it, you get the answer, and now you have shear. Now you make it a little bit harder. Now you start getting shear.
But now you cannot say that this is SH mean this is SH1, except if you have principal stresses.
Yeah. I mean, if you say SH mean and SH max, it sort of guarantees that they are principal. So it's a S11, S22, S33, and then you have S12, S213, whatever, 31. It goes like throughout the system. And you have, it can be very complicated. That's the beauty of the Andersonian faulting theory. It makes everything easy.
Anderson, yes.
Yeah, mathematically easy in particular. But yeah, it can get very, very complicated with this. And to be honest, I don't expect anything much crazier than this for exams or something. It won't get very, very mathematical. I don't think it's going to get very, very too mathematical on this regard, because many places they just use Anderson for simplification. It's just you need to be comfortable in moving from one coordinate system to another. Not coordinate system, the configuration to another quite easily. And Euler's matrix is the answer. I mean, if you take a linear algebra class, they do that without the application in theory. Even aerospace people do that. I mean, but they use a different system. They don't use northeast down. They use northeast up, I think. It's the other way. Because our inclination is from the vertical down, their inclination is from the vertical up. Anyway, any questions before I move to the next subtopic, which is gonna be easier? So it will be about, okay, we talk about SV, SH max, and SH min. We learn about those Andersonian stresses. Now we have to be able to quantify them. Okay, how do we quantify the magnitude of these stresses in the field, like in application? And we are gonna start from the easiest one. Well, not the easiest one, the easiest concept-wise, which is that of SV, the overburden stress. So overburden calculations are used to estimate SV. We call that the lithostatic stress gradient. It has to do with the ancient Greek word for rock, lithos. And rule of thumb, rule of thumb which you can use if you don't have any other information, perhaps. It might be safe to use if you don't have any other information available, of 1 psi per foot. This translates to 23 MPa per kilometer in SI units. Every kilometer depth, 23 MPAs. Every 1 foot depth, 1 psi. Now this one is not a mathematically derived quantity, so it's not an idealistic value, it's an approximation. For the depth that we are looking at and the areas we are interested, 1 psi per foot makes sense. It's not an amazing approximation, but it's an easy and it's good. Now, when you are doing overburden estimations, which is a sub-discipline of structural geology, this is the equation you are solving. You are adding up every rock layer above the point of your interest, the weight of that on top of each other. So if I have 10 layers, if I'm trying to measure SV at this point, and there is 10 rock layers above it, I get their mass, I add it up, that will be SV, right? It's gonna be in units of PSI, so pounds per square inch. And basically, I find that. But mathematically, what I basically do is solving this equation. I'm talking about the integral, solving this integral. I take the density of each layer, I multiply by G, and I integrate with respect to D from the reference depth to the end. Okay, just like the example I have, or the example, the schematic I have here on the left, on the right, sorry.
It's all GH.
Yeah, row G, basically you're solving row GH, but there is several rows and several age intervals.
Different layers.
Yeah, one for each layer. Now, approximation coming from the trapezium rule. You can do like sigma. Basically, it's the same thing, but the sum. You get the layer one. How much does it? What is its density? It's row one. I multiply by the
2.5 and row carbonate.
Yeah.
2.8
and you can go on. Yeah. Big major subdiscipline in geology overburden estimations. In fact, our chair for his postdoc, he did it in NASA, and I believe he did overburden estimations for. He was done with the Earth, so he did other planets, you know. But it's basically they are all solving this. They are all solving this equation. Okay. And this is the expanded version of the summation. You have raw bulk of layer one times the height, which is layer one goes from Z0 to Z1, right? And then, yeah. And then second layer goes from Z2 to Z1, right? So the height is Z2 minus Z1. Now something I want to say to the foreign students, because I had an issue too when I came over to the US. If you use American units, and I said that in the other class, and you go from pound mass, which is the density units, to you want to go to pound force for the PSI, okay? You don't need to worry about the G, because 1 pound mass becomes 1 pound force in atmospheric conditions. You don't need to multiply by G. If you go and find G in American units, it's going to be 32.2 feet per second square. Now, but 1 pound mass does not exert 32.2 pound force. It exerts 1 pound force. So if you are using American units, you need to omit the G. If you are using PSI, if you are using SI units, you have to use it. Wait, I have there is a question in the chat. I didn't see it. Sorry, Joseph. Oh, he said hi. Okay. Hi. Hi, Joseph. Yeah, but we're gonna see that next time in more detail. But please be very careful with what unit system that you are using, because you may be using the unit where it has pound mass, the density is given in pound mass, then don't worry about pound force. Don't worry about G. But if you are using kilograms per cubic meter for the density, to get to newtons and therefore Pascal, you need to multiply by G. So 1 kilogram exerts 10 newtons, roughly speaking, right? But 1 pound mass exerts 1 pound force. So I had issues when I was my first semester in the US when I was taking statics, and we had like a quiz every week. In the first weeks, it was taking me a while to figure out how to go from pound mass to pound force. So it can be confusing. But yeah, basically you have the density and the height of each layer. And then this one, the first height is Z2 minus Z0, Z2 minus Z1, Z3 minus Z2, Zn minus Zn minus 1. And you put those here with the density, and you will find what is the value of SV in PSI. And we will proceed next time about some more complicated examples like offshore. Yeah, you have the water above it, so you have an additional complexity. Yeah. Thank you very much. Have a nice rest of your day. Hi, Joseph. Do you have any questions? Okay, pause, stop recording.